Hi everyone. Thank you for being here today. My name is Mathieu Tarral. I'm really excited to be at Insomnihack with you. And welcome to this talk. We are going to talk about debuggers and hypervisors. But mostly what I would like to talk about is how we can explore the possibilities of using the hypervisor as a new kind of debugger, a flexible debugger in this case. Before we begin, I really hope that the CTF is doing well for you, if you are playing. I'm not a CTF player myself. I'm just asking this question because I heard that you had really tough challenges in the past years. I'm speaking about challenges like Escape Me or Abyss 1, 2, 3. These type of challenges are really tough because you are given a custom hypervisor based on KVM, and you had to exploit the VM. Now, what's really particular with these challenges is that you don't have any debug API into the VM. So the hypervisor doesn't really help you to debug the VM. You have to rely on exploitation. So I will start with a disclaimer. I cannot really help you with these challenges. I cannot help you if the hypervisor doesn't provide you a debug API. What I can do, otherwise, is try to show you what can be done if the hypervisor provides you a debug API, which is virtual machine introspection. And how can we make the most out of this API, and how to leverage them to build flexible debuggers. So, first, who am I? What's my background a bit? I'm an ex-F-Secure fellow, and I've been working on building stealth and hypervisor-based sandboxes in the past. So the technology under that is virtual machine introspection. So I've worked on it a bit. And along the way, I've built the KVM VMI community, which aims to bring standard and unified VMI interface on KVM. And the reason I'm interested in debuggers is because I've seen what malware sandboxes can do when they are based on the hypervisor. And on the side of debugger, we are still debugging the VM. So we are not using the full capabilities of hypervisors in the case of debuggers. That's how I became interested in the topic. So our agenda for today, first we're going to a bit explain why debugging from the hypervisor is interesting. What are the concrete use cases? Then a bit of history. What are the different projects that you might have heard of? The challenges that you need to face, of course. I will do a quick demo of the project I'd like to present today. Then we'll talk about hyper breakpoints from the hypervisor. What is the state of them, and how we can do better for our debuggers. And then a bit of talk about the future. So let's start. First, why? Why do you want to debug from the hypervisor? What are the concrete use cases, and why I think they are going to become more relevant in the future? Let's start with the most obvious one everyone can think of. Your debugger will always have a side effect, an observer effect. And if you think about malware analysis, that has already been the problem. Because your traditional debugger will have no real stealth. If you try to debug a process, the debugger will always leave some structures modified in the environment of your process. It will alter the syscall behavior. They will return different values. And your breakpoints sometimes will be visible. So to analyze advanced malware, it's a real pain. And the robustness also. We don't think about it, but the debug APIs from the operating system has been designed in the 1990s, and there was no malware at that time. So the malware use case has never been taken into account. And also the debugger will run in ring 0 sometime at the same privilege level as the malware. So we'll just fight each other to gain control and to place hooks in the system. So we are just fighting malware at the same privilege level. So we can't really win. So that was the first use case, malware analysis. Then what you have is that sometimes this debugger effect is intentional. Think about what operating systems can do if they don't want you to debug some of their features. I'm thinking about here the protected media path, which has been introduced since Windows Vista, and which is used to enable the DRM content on your computer. So they don't want you to reverse this kind of and debug this kind of features because it protects the DRM. And if you think about new security features like patch guard, well, debugging patch guard is hard because when you enable the debugger and you switch Windows into debug mode, patch guard has to disable itself. Otherwise, it will just try to fight with the debugger. So debugging patch guard is a bit complicated when you are in debug mode. And going a bit further, what you have today is an incomplete system view. What you see here is the Windows Virtual Secure Mode from Windows 10. In terms of debugging, I'm thinking about incomplete system view because today what you have in WinDBG, you have extensions to debug the state of Hyper-V. You can read-write the full memory, but you don't really have an easy way to debug the secure kernel here, which is isolated. So you have to do your own breakpoints and stuff. So it's a bit complicated. And we can conclude that today's the debuggers are in a way fighting with the new operating system security features in the case of Windows 10. So we'd like to gain back some control over that. Another use case interesting to debug from the hypervisor is the boot sequence analysis. What you can see here is the boot sequence from the BIOS. The BIOS will run the post test, then loads the MBR, which itself loads some code from the active partition, and then loads the bootloader, which is your grub or NTLDR for Windows. What we can do here is use a USB stick and boot from USB. In this USB, I can load my kernel into memory, which will be my hypervisor. And this kernel, this hypervisor, will create a virtual machine, and his first instruction will be a BIOS interrupt. The interrupt 0x19. It's a specific kind of interrupt that tells the BIOS, hey, can you just reload the first device, boot device that you can find? And usually it's the hard drive. So we are restarted the boot sequence, but this time we are in a virtual machine. So we virtualized our boot sequence, except for the post test, of course. But for the rest of it, we can fully analyze it under a hypervisor. So it's quite convenient. In the case of UEFI, I haven't digged into it, but it should be also possible. And another interesting use case is unikernels. In fact, I didn't know when I started working on this project that unikernels was an interesting use case. But if you think about it, unikernels, they are specialized embedded system images. So you take your kernel and you take your application and you merge it into one, let's say, application. And the kernel is stripped from any unnecessary dependencies, like there is no scheduler, there is no runtime, there is no tools on it, and you strip it from everything so that it boots faster. But everything runs in ring 0 at the kernel level. And it's only one process and one address space. And of course, the consequence of that is that there is no debugging stub. So you may have to rely on the hypervisor underneath it. So another interesting use case. But apart from these very specific use cases, malware analysis, unikernel, etc., it's convenient to debug from the hypervisor because your guests are unmodified, untouched. You don't have to go into the guest, install the Windows SDK, and switch the guest into debug mode. So you change the hardware sometimes because you have to introduce a serial cable or something, and put the system into debug mode. So we can debug your VMs on the fly. So, which is really convenient. And if you could look a bit further, what you get is cross-platform debugging. Basically, you can debug Windows, Linux, or macOS from the hypervisor, and you have a unified debug framework, and you can build your scripts and your knowledge on top of just one tool, which is quite cool. Now, and the last interesting thing is that we might also want to follow the malware sandboxes trend. Nowadays, the malware sandboxes, they are hypervisor-based. If you think about VMware, or Sandbox, or Trackproof, if you've heard of it, these are all sandboxes based on hypervisor using VMI, like we said, and they have demonstrate that it's really interesting because they are cross-platform, they are agentless, so you don't have to maintain the virtual machines or provision them, and they have demonstrated how to get stealth breakpoints, really stealth. And also some interesting features like process hijacking. So I'm just targeting one process in my VM, for example, explore.exe. I'm hijacking the execution and I'm injecting a code that will call an API, like a create process. So I'm directly creating a new process from the hypervisor. Again, really interesting. So if you want to do a bit of recap on the why, concrete use case is malware analysis, advanced malware analysis, because you don't trust your operating system debug APIs, or you don't want to rely on them. You want to rely on something a bit lower level. And the boot sequence and unique analysis are concrete use cases. And the convenience of having unmodified guest and a unified tool for operating system debugging. And for all of these reasons, we want to leverage the hypervisor as a new debugging platform and exploit the full capabilities of it. Now a bit of history. I'm not the first one to look into this topic. There have been plenty of projects. And now we are going to try to look at these different projects, what they are doing, and if they are the same categories, are they maintained, etc. So I try to do a bit of a timeline from 2003 until today. This is all the hypervisor level debuggers that I could reference, starting from QEMU GDB stub to today. So they are not all the same. They are doing the same job. So let's draw some categories about it. What categories do we have? First, the built-in hypervisor debug stub, the thing that you have in your hypervisor at VMware. You have some bare metal debuggers to debug a physical machine using either hyperjacking or USB boot. And you have the virtual machine, which I mean by debugging virtual hardware debuggers. And in this case, this category, you have either emulated or full virtualization. But let's start by the debug stub and why we can do better. This is your traditional debug stub in your hypervisor. The problem is that they have no real stealth. They just set a traditional 0xCC in memory, and it can be read, so detected. You can have hidden breakpoints, for example, with VMware, with this configuration, but it's using the debug registers, so limited to 4 breakpoints. There's no real guest awareness. What you can do is debug the kernel, that's made for it, but you can debug user and application and understand their context. And there's no real flexibility, because it's GDB only first, and it's tied to one hypervisor, so you can go really far. That's why I would like to improve the state of this debug stub. Then another category is the bare metal debugger. The role of these debuggers is to debug a physical machine, but using a hypervisor. So in this category, you have the category is hyperjacking. So the terminology is a bit weird, but it just means that you are virtualizing your host on the fly. So you load the driver on your system, and this driver will just virtualize your entire system on the fly. So the first category is HyperDBG in 2010. And then you have VirDBG. So HyperDBG, what they wanted is to debug production systems. You just press F12 and you have a debugger pop-up appearing on your machine. And VirDBG, they wanted to debug a patch card, basically, using DMA attack. And in both cases, the problem is that you have to develop a driver for your operating system to do this hyperjacking, so it's not really OS agnostic. So that's why they have been discontinued. Second category is USB boot. This is more interesting because you are just boot. That is what I've just described in the Y section. You take a USB boot and you boot on the hypervisor, and then you virtualize the boot sequence. So you have RAMUFLAX in 2011 and PearlsDBG. RAMUFLAX is based on BIOS, and PearlsDBG is based on UEFI bootloader. But both of them aim to debug physical machine using the USB. So these are more interesting, I'd say. Next thing is virtual machine debuggers using emulation. Maybe you've heard of this one, Pyrebux from Cisco Talos. It's really interesting because it's using emulation, it's using volatility to reconstruct the state of the guest, and it has an IPython shell, an advanced IPython shell, and you can set really fine-grained callbacks. You can set callbacks if your page is being read or written, and it's really meant for malware analysis. But the problem is that it's emulation, so it's a bit slow. And that's why I didn't look into it, because I want to use the full virtualization. Now about full virtualization, what do we have? This is my point of interest. I would like to debug my malwares, but running fully virtualized with full virtualization speed. First, we have unmaintained projects, like people trying stuff, and yeah, well. First is VMI DBG. In the concept, is really interesting. It's a GDB stub on top of the VMI, which abstracts from the hypervisor, and then you talk to the hypervisor. But when I wanted to try the project, it didn't really compile, and it had no real documentation, so I didn't look further into it. I guess some of you will know RVMI from FireEye. This one, it's KVM introspection, and it uses Recall as both the shell and the introspection layer. So it's quite smart because you leverage Recall as a memory forensic tool and using as a debugger interface. But again, I haven't seen commits in RVMI since 2 years, so I don't know what's the state of it. Then what you have, maybe you've heard of Winbagility in 2016. They wanted to make an instrumentation of VirtualBox. Why? Because VirtualBox is open source and it's cross-platform. You can have it on Linux, macOS, and Windows. So let's put some VMI into it. And they have developed KD stub, choose WinDBG, and to debug VirtualBox. And then later, the same team built Soundbagility, which is the malware analysis framework based on Winbagility to leverage the work they did. One thing to mention is that the Winbagility team was really, really focused on performance. They wanted to put breakpoints on the memory allocator of the kernel, so it had to be really, really fast. That's why they didn't consider the idea of using abstraction libraries like libvmi. And that's the reason why I didn't consider the project at the time. Because my objectives were not emulation or bare metal debugging. I wasn't interested. I wanted a flexible debugger, but running at the full virtualization speed. And I wanted to be compatibility about performance. So last year, I built a debugger on top of Radar, and leverage Radar as an introspection tool, and also based on libvmi. And then I built the project I'm going to present today, which is PyVMI DBG. It's a GDB stub based on libvmi, which then talks to the hypervisor. So I'm not looking for performance here, just compatibility. And also I'm trying to build a guest-aware debug stub. Now looking at the challenges, if it was this easy to build this kind of debuggers, well, you'll be using them every day to debug your applications. But it's not. There are many challenges. And the first one is that you will need to rebuild the debugger API. Why? Think like your normal use case scenario when you GDB attached to PID. Well, you just talk to the kernel, and the kernel knows how to find the states of its own processes. He knows where to find the threads and read their context state. And you are doing this over an API, a clearly defined API, in this case, Bitrace on Linux. When you're doing this with virtual machine introspection, first, you don't know the operating system. You don't know what it is. And second, you have to read and interpret raw memory structures from memory. So it's much more complicated. Your API is just read memory, read registers, and then make sense out of it. So that's one of the first big challenges. Now to face this challenge, what we want to do is to fill the semantic gap. How can we do that? What we need is an intimate knowledge of the guest. We need to understand what it does, what it is, and where are the structures in memory and the functions. And if you think about it, this is a really big job. But it's not our job. Like, there are already tools out there that are meant to do this, and they are doing this very well. So I'm thinking about memory forensic tools. And if you look at what Recall can do, Recall can build profiles. It can analyze memory dump and give you a JSON profile out of it. So it gives you the constants, the functions, and the structures in memory, which are all offsets from the kernel base address. So with this, you can already fill a bit the semantic gap. You analyze your VM, you take a memory dump, analyze it with Recall, and Recall gives you this parsable JSON file that you can use. So we already filled a bit the semantic gap. But it's not the only challenge. What we have to do now is also to follow operating system changes, because they change over the course of time, of course. Your debugger might well support Windows 7 but crash under Windows XP or crash under Windows 10. And the reason is simple, because these operating systems are changes. They are changing over the course of time. So if you want to have an example, on Windows or Windows XP, the ideal process is running outside of the main process list. So sometimes we just post the VM, you will wonder, what is the current process doing? And you won't find it in the main process list because it's the ideal process. So you have to build this, add some logic on top of it to handle these cases. In Windows Vista, they made some big changes in the kernel. And Windows 10, as you know, there is the virtual secure mode and the secure kernel. So it's a bit more complicated. And if you go a bit further, if you want to adapt on Linux and macOS and build a flexible debugger, well, you have to adapt to any operating system configuration out there. So that's what's the real challenges. But however, it's not that difficult because the core operating system internals, they tend to not change. I mean, an in-process an e-process and e-thread on Windows is still the same from XP to 10. I mean, the structures, they change, but the core fields are the same. So we can use that. Now, regarding the issue that I wanted to be hypervisor agnostic, what can we do? Well, I was speaking before about libVMI. What is this libVMI? It's a library, virtual machine introspection library, and it will make an abstraction layer on top of the hypervisor's interface. So it has functions to deal with low-level stuff like parsing the page tables or intercepting hardware events and translating them. And it unifies the interface on top of the hypervisor's VMI APIs. And also it offers some basic introspection, and it supports record profile, exactly what we want. So I can just specify my record profile, my VM, and I can use libVMI to translate my symbols directly. And will make sense out of it. So what is the support, hypervisor support for libVMI? As of today, Xen is fully supported in terms of VMI. You have registers, memory, and all the hardware events that you can think of. Interrupts, debug events, etc. And KVM is on its way. There's Bitdefender working on a patch to bring VMI and to already bring a VMI interface on KVM. So let's do a bit of recap of our projects now in terms of flexibility. First, I'm going to use VMI to query the hardware state. Then I'm using libVMI to be hypervisor agnostic. I don't want to rely on my hypervisor. Then I'm going to use the record profile to make sense of this raw data and read the structures in memory and make sense of it. And then I'm going to use the GDB protocol because I want to use any GDB front-end on top of this thing. And now let's talk about a bit of a demo. What I'm going to demo to you today is this project that I've been working on. It's PyVMI-DBG, so it's coding in Python. It's a GDB stub on top of libVMI, which aims to bridge the gap between the front ends and the hypervisors. So how does it work? You just specify a port, a VM name, and a process if you want. It has two modes. One that I will call the raw mode, or the raw debug context, where your process is just assimilated as the entire system. It's what you have normally in a GDB stub. So a thread is assimilated to one vCPU, and when you attach to the VM, it just posts the VM, so not really intelligence. And then you have the guest aware mode, where you specify a process. So you have Windows and Linux debug context. And what it does is that it tries to find the process descriptor memory and then read the thread state and read their execution context and report them. So like if you are debugging on the guest, exactly. So basic software breakpoints are implemented. They are not stealth as of today. You have single step and breaking. Breaking is what you continue the execution and then you hit Control-C and say it stops the guest again. So let's do a bit of a demo. I think I need to switch my system so that I have duplicated screens. Synchronize, yes. No? No? Great. Doesn't work. do something. I'm trying to unify the output because otherwise, if I type in my terminal, you won't see anything. Okay, it doesn't work. Great. Maybe I can use the built-in demo I've done for this purpose. No. Yes, that's what I wanted. Okay. Okay. Can I start the demo here? Yes. Okay. So this is a demo of the raw mode. It uses the VM like your GDB stub from QEMU. So this is my Windows XP VM. The reason I have Windows XP because I'm using Vagrant to keep my environment clean, and the problem is that I'm virtualizing KVM on Xen on top of KVM, and you cannot run Windows 7, Windows 10 guest yet. So I'm using Windows XP for this demo. So my Windows XP is running, everything's fine. So what I'm going to do now is to go to the Vagrant VM and start my debugger in raw mode. Okay, so this is, I've put some more arguments because I wanted to listen to 000 because I'm looking from the outside. And then just starting the debugger here. So I remove the process information because I wanted to use the raw mode. And then I'm going to start GDB and use the target remote stuff to connect to the debugger. Okay, so now we are attached to the debugger. And if you look at the output, there's plenty of output. It's just the GDB protocol over here. But if you look at what the output was, it's the raw debug context. That's not really more information. Okay, so I'm going to do some single steps to move to a single step execution, and everything is not on top of libvmi, of course. And then I'm going to try to set a breakpoint at this address. Yes, I need a star. Okay, and just continue the execution. Okay, we hit the breakpoints. Great. And I think I'm just continuing the execution over here. So yes, okay. So the demo is done. So that was just the raw mode. That's what you already know because it's using it's like the QEMU GDB stub. Sorry. So now the guest aware. We have a bit some intelligence into it. This time I'm going to use Radar 2 because it's more interactive and I like it as a chill. So I'm going to start a CMD command over here. I'm going to start my debugger and I want to intercept CMD. So at the end I'm just specifying the process as CMD. So my debugger is listening. And then I'm starting Radar 2. Okay, I'm connected. So if I look at the outputs of the debugger, it locates the process and the threads, the first thread and the ready states. So now if I go back to Radar 2, I can do dpt to list the thread. There is one thread. And I can display the instruction, of course. So I'm loading some symbols, the kernel and TDLL to have semantic meaning. This. Okay, so now I have some symbols, so it's more interesting. I'm going to look into my symbols and look for the anti-open-file function, like this. So so it's there, it's loaded, and I'm going to set a breakpoint on this function. Okay, so now I'm going to type the dir command. Okay, here I'm demoing the break-in function. So you continue the execution and then you hit Ctrl-C, and if you go back, it intercepted again the thread and the process. You can see there's a break-in here, like there, and it attached again to the process state. So now I can put some breakpoints. with db. I tried only the anterior symbols. Yeah, there was a bug at this time order too. So I had to put the breakpoint manually, I think. Okay, so I'm just pasting the address here with db. Yeah, this one. I'm setting the symbols on anti-kernel, anti-open file, and continuing the guest execution. So my breakpoint is set, going back to the VM, attaching it, and let's type the dir command. Yes, we hit our breakpoint. Great. We can continue the guest execution with array, and breakpoint hit another time. And you can see the display of the dir command on top of it. So it's debugging from the hypervisor, using libvmi. Can see what. Okay, so that was for the demo using only one process and one thread, and here I'm demoing again with where is the? Because yeah, I'm starting Microsoft Paint here, and you can just see that at some point I can list all the threads. So if I go here, yeah, I'm in dbt and I can see all the thread state, and each time there is a breakpoint which will be it, you will have a different thread which will be highlighted because it's this thread which executes the breakpoint. Okay, so that you can see that the thread is selected here with a little star in order to, which means that it was this specific thread which had the breakpoint. So that's it for the demo. It's a guest-aware hypervisor level debugger based on libvmi. So I know it ain't much, but it's honest work. I've done this on my free time. But what can we do in the future? What are the improvements? Improvements. So you can have more information about the proc, the process with infoproc. This is some GDB command to implement, also shared libraries. These are all command that you can implement. And then I'm thinking about everyone that wants to develop on this project. I'm a really big fan of Vagrant because developing on top of Xen is a bit of a pain. You have to run a modified hypervisor, then you have to run VMs. I want to make it as easy as possible for you to join the project. So my Vagrant environment has Xen installed, either package from source, libvmi, libvirt, and some VM with the recall profiles configured. So it's nested virtualization, and you can get it from here. Now, a bit of talk about the hyper breakpoints. I was mentioning that we're not using the most advanced breakpoints out there for our debuggers, and it's the case. So let's do a bit the state of hyper breakpoints. When I'm speaking about hyper breakpoints, what I mean is just a breakpoint using the virtualization layer. It's a term that's been introduced in the Winbagility article at the STIC in 2016, and yes, we're not using the best breakpoints available. The first breakpoint that you can think of is the most basic one. You write your breakpoint in memory and you listen to interrupt 3 events. And if there is a breakpoint, if there's a hit, you just restore the opcode, you single step, and then you restore your breakpoints and you continue. So it's quite fast, but it's not really stealth and it's not safe. And by safe, I mean that's safe in multi-vCPU conditions. If you have another vCPU which is running at the same time while you are doing this kind of a recoil thing, while you're restoring the opcode, well, the overseas vCPU might just execute on this instruction and miss your breakpoint. So it's not multi-vCPU safe. To gain this multi-vCPU safety and avoid this race condition, we can pause all the vCPU at each event. That's what you can do. It's a bit less fast, but this time it is safe. Also, you have hyper breakpoints, the same breakpoints but from the hypervisor. You inject set your breakpoints in DR0 to DR3, and you listen to interrupt 1 events. So it's the fastest ones because you are comparing registers, so it's really, really fast. And this time it is safe because each vCPU has its own copy of the registers, so there's no overlap. And how can we gain stealth with this? Well, you can listen to move to DR events, and you can restore the guest value, single step, and restore your own value. So you can fool the guest into thinking that there is no breakpoints. So yeah, we have the fastest stealth and safe breakpoints. That's great, but wait, there's only 4 of them. So we can't go very far. So let's look at another type of breakpoints, the page hyper breakpoints. You have the guest virtual address, which is translated to a guest physical address and then to a host physical address. This thing is done using the extended page tables. First you need to find your guest virtual address, and from this you need to find the guest physical page, and you translate it via the EPT to find the host physical page. And with this host physical page, you change the permissions and to generate EPT violations. So you can change the permission to have events on read, write, or execute. So it's not really fast, but it's stealth this time, and it's not safe. Why? Because it's not fast because you have a very high overhead. On your whole page, you will have a lot of events where you are just going to say, no, single step, I don't want this one. It's not safe because the EPT are shared by all the vCPUs. So when you are relaxing the permission to continue execution, another vCPU might just go there and miss your breakpoint. So it's not safe. And also about the question, should you single step or emulate? Well, emulator are a bit of incomplete. It's very hard to do a full x86 emulator. There are a lot of vulnerabilities because of the complexity. And if you emulate a lot of instructions at the same time, this can lead to instabilities. And this has been seen in production. So always use single step if you can. So where can we go from here? We can do new types of breakpoints. Yes. So what we can do is soft hyper breakpoints, but new ones. This is a representation of the EPT. You have your guest virtual address, translated to a guest physical address in the guest, and then using the EPT from the processor to translate this to the page on the host. What we can do is first we duplicate the physical page, like this. Then we can set our breakpoints on this second page. We can set this page as execute only and the other one as read write. And then we can point our address, our page table entry to this new page, which has the breakpoint. And if there is an interrupt 3, well, you just handle the breakpoints and you log it. If you get an EPT violation because of read write issues, then you just switch back to the first page. And if you get an EPT violation because of execute problems, then you just switch back to the breakpoint. And then you can have a breakpoint which is fast, stealth, but again, that's not safe. But we already have a fast and stealth breakpoints. So it's quite interesting. But we can do better. We can do an advanced soft hyper breakpoints. Again, you have the EPT here and your page. We are going to work at views at the vCPU level. In view, I mean in memory views. First, this is your vCPU, which has an EPT pointer pointing to the beginning of the EPT tables, translating to your page. First, we're going to duplicate the EPT, like this. We have a second view, EPT view 2. And then we're duplicating our page and pointing to it, putting a breakpoint, changing the permissions, as before, read, write, and execute only. We're pointing our page table entry in the second view to our breakpoint, and we switch the vCPU to view 2 to really hit the breakpoints. That's what we want. And this is our initial configuration. We are not going to hit the breakpoints. If you have a breakpoint, you just handle the breakpoints. If you have an EPT violation because of a read-write, you switch back to the read-write page, but this time you switch at the vCPU level. You switch the external page table pointer. This is really important. And if you have, again, an issue with execute, you switch back to the second view to execute the breakpoint. So you switch back memory views at vCPU level. And what you gain from this is that this time you have fast, stealth, and safe breakpoints. Safe because the EPT pointer is specific to the vCPU, so there's no override. Great. We have the best breakpoints out there. Fast, stealth, and safe. So this type of breakpoints, they have been implemented in Xen. So Xen 4.6 implements alt P2M, which allows which opens an API to change this EPT pointer. And they have been implemented in Darkproof in 2016 for stealth breakpoints and multi-vCPU safe. So that's the best breakpoints you can have today, and we are not using them in our debuggers from the hypervisor. Now a bit about looking into the future, where we might go from here. This is the vision where I would like us to go. A flexible full system debugging in 2020. So on the one side, you have your favorite debug front-end, your IDA, Radar, Visual Studio, and on the other side, you have the hypervisors. And VMIDBG, or PyVMIDBG, is bridging the gap between these two. It provides a new debugger framework based on the hypervisor, so it's flexible. You can adapt to any operating system out there, and it's a unified framework across all the hypervisors. And you can also extend this concept for the BIOS debugging that we have seen earlier. So to projects like RamoFlax or PearlsDBG, same. You keep the same debugging framework and infrastructure that you build on top of these embedded hypervisors. So a unified debug framework. What is the future of libVMI about the design? Let's discuss about it. First, the project has been recently switched to CMake, so you can now build it on Windows and build Windows drivers for Hyper-V, VMware, VirtualBox on Windows if you want. And the project has now, let's say, new ambitions and new goals. The goal to be cross-platform and to run on Windows, macOS, and Linux to support these hypervisors that you have there. There's the embedded use case, where you want to be embedded on a USB key for RamoFlax and PearlsDBG. And there are safety concerns. The problem is that, as you have seen before, my demo was running with sudo. I was using sudo because to access the Xen API, you have to be root, because Xen is running, the Xen tool stack asks you to run as root. So libVMI, in a sense, needs very high privileges, and it needs to be safe. And also it processes untrusted input, and if you think about, sometimes it's dangerous, because if you think about my use case, it's likely dangerous. So the long-term question might be, should we implement this project in Rust? It's an open question. It has just been open a few months ago. So it's really to be discussed, and if there are Rust developers in the room, please come talk to me. I really like to have a chat. Then how you can get involved in the project. First, if you have a hypervisor developer, well, please open a virtual machine introspection API. This has been demonstrated how useful they are. So please open a VMI API. I'm thinking here about VMware, Hyper-V, or VirtualBox. Please open just an API so we can build our tools upon it. If you want to work on libVMI, well, there are drivers to be written to improve the compatibility. You can improve the introspection capabilities to query the process states in memory across Windows and Linux. And you can also work on performance study, because Winbagility folks, they didn't want to use libVMI because it was too slow. But at the end, if I want to have this vision where everyone is using libVMI as a unified debug framework, you might want to have it as efficient as possible so that everyone use it. And also rewriting in Rust. That's the question I asked before. You can look into it. And for PyVMIDBG itself, well, you can always improve the GTB stub. There are other steps to be written, LLDB or KD, if you want to use WinDBG or other debug frontends. And if you know about Windows or Linux internals, about the scheduler, how the context switch is working, how the process state is stored in memory, well, also please come talk to me. And you can join the Slack, ask me for invites, but we are organizing our work from there. My conclusion for this talk is that first, for hypervisor developers, I would like to build a unified framework for debugging. And I would like to leverage the full power of our hypervisor and focused on these abstractions together to facilitate the work of others. If you are a virtual machine user, well, I would like you to see your virtual machine as a new process tree. It's not an opaque container anymore. The virtual machine introspection APIs have done that. They are not the VMs are not fully now fully introspectable and inspectable, so you can debug them and you can see them like a transparent container. And also keeping the same environment. If you are researching on Windows, Linux, whatever the version, I want you to keep the same environment and debug this from your host. And well, for everyone, I would like to say that our hypervisors have demonstrated their unique capabilities for sandboxing, and I would like us to use them to build a new debug framework and make it as a commodity for everyone. Thanks to all of these people, some of them work at Microsoft, from Twitter, from everywhere. They helped me build this talk. Thank you so much for them. If you have questions, I'm available. Thank you for your attention.
Thank you, Mathieu, for your talk. So if there's any question, please raise your hand, and
yes.
I will give you the mic.
There's one there.
Hi. Thank you very much for the talk. I have a question about performance. Can I insert like 100,000 breakpoints and introspect it in a normal amount of time?
Well, about performance, the WinBag80 folks, those who are focused on performance, they say they could reach like 21K breakpoints per second using their KD stub directly connected to a VirtualBox with VMI. So they say what you can do from the hypervisor. It's what was 21K per second. On my side, I'm not targeting full performance because I want to keep this compatibility layer. I want to do sometimes a bit of debugging, but not tracing, like what you can think of. But I think you might want to look at the WinBag80 project to see what they have accomplished with performance. And what we can do with libBMI is, for example, use /dev/shm for share memory for the access to improve the performance of this. And there's work to be done, like I said, on libBMI. But look at WinBag80. I'm sure you can find your answers about performance.
Any other question? Yeah, I see two there.
Hello. Thank you for your talk. I was wondering, the part about motivation, you described, for instance, like malware analysis and the lack of side channels of these kind of approaches. I mean, side channels, like actually side effects and, that kind of stuff.
Yeah, well.
That can, of course, be fixed. Like, I'm talking things like timestamp counters and, things that...
Oh, yeah. I'm sure this has also side effects because you're debugging for the hypervisor. Yeah. What I meant as debugging side effects was more about, for malware analysis, I wanted to be able to tackle this anti-debug issue we have. We're not going to solve the anti-VM, of course, but at least if we could solve this anti-debug issue that we have with the debugging APIs, like being visible, it will already be a great step, I think. Yep. So yes, it has side effects, right, of course, but my point is say, okay, let's solve already the anti-debug, and we can see that even if you remove the malware use case, it's already really convenient to debug from the hypervisor to debug anything you want.
Mm-hmm. Yeah. So my actual question is that those kind of things can be technically fixed, but fixing such an issue would imply a hypervisor-specific patch. And for instance, the problem
you mean the virtual machine introspection API to open them?
I mean, if you want to fix something like detection via timestamp counters, like differences that
this is anti-VM, so
so basically, when you present hyper breakpoints and how some Xen, for instance, implemented that, that's something that is hypervisor specific. Doesn't work across all the set of hypervisors.
Yeah, that's why we need to develop this VMI API, and it was like a bit of a call to everyone to develop this standardized interface to work with the same breakpoints, all of us. But, okay. Thank you.
Hi, thanks for the talk. You mentioned execution breakpoints.
Yes.
You could also do the same thing for read-write breakpoints, right?
What do you mean?
Basically, break on read of memory.
From a page. Like you have, I said that you had like fine-grained breakpoints because you could remove the bit which was read, write, or execute. And yes, you have this flexibility of fine-grained breakpoints with page hyper breakpoints. Yes.
Any other question?
Right there.
How does it work if the guest is not running in protected mode?
Is not running in protected mode?
Yeah, for example, it just at the start of software, when it's running in real mode and you are trying to debug, it's
Well, the hypervisor has to emulate this real mode, I think. This is a bit technical. I haven't developed a hypervisor myself, but I think that in the early stages of the boot, if you want to do this boot sequence analysis that we've seen earlier, the hypervisor has to emulate the real mode, I think.
Yeah, okay, but can you still debug that through the libdm?
Well, that's what Ramuflax was doing. So you can check the project if you want. There is a paper. So they said they were debugging BIOSes and physical machines. So yeah.
Thank you.
Please check the project.
Okay, we have time for 2 more questions. So there's one.
So you said that emulation can have some kind of instabilities. What do you mean by that?
So if you emulate multiple instructions at the same time, in a sequence, this could lead to instabilities. There's an article on that on the Xen blog. I haven't it in mind, but I can give you the link to the article, which was there was a bug on the mailing list that a guy used emulation to emulate a page multiple times, and his Windows just crashed because of it. So heavy emulation can lead to instabilities. That's why. I can give you the link after the talk if you want.
Last question. The first I see the. Okay. No questions? Okay, perfect. So thank you again, Mathieu.
Thank you.